Alright, the final topic, circular motion. What is circular motion? Circular motion is basically the movement of an object along the circumference of a circle. So it's moving in a circle. So it's moving along, yeah, it's moving like in a circle path. It can be both horizontal and vertical. An example for horizontal circular motion is merry-go-round. You definitely played it before. For vertical, it's a roller coaster. Yeah, like a roll is a vertical circle track. It's kind of scary. And now, what are some specialities of a circular motion? We're going to talk about the specialities in uniform circular motion. What is uniform circular motion? It's basically an object moving in a circle track and is moving at a constant speed. So the first speciality is constant speed, but speed, but changing velocity. Oh, you may ask, oh, isn't speed and velocity both describes how fast an object is? Well, that's correct. However, back to the unit 1, speed is a magnitude. No, speed is a scalar, but velocity is a vector. So let me give you an example. An object is moving in a circle path and given a point A, point B, point C. Yeah, the object is moving with a constant speed of 3 meters per second. So for speed, yeah, it's the same because it's going along a track with 3 meters per second. That's a magnitude. However, the velocity is different. At point A, the velocity is pointing that way. At point B, the velocity is pointing that way. At point C, no, wait. At point B, it's going that way because it's going counterclockwise direction. At point C, it is going that way. Let's pull these three vectors out. This is vector A. This is vector B. And this is vector C. Are they different? No, they're not. Are they same? Are they the same? No, they're not the same. Because how how would you know two vectors are the same? How do you determine two vectors are the same? The first thing is same direction. Are they in the same direction? No. And the second thing is if they have the same direction, are they have the same magnitude? Do they have the same magnitude? Mag Yes, they have the same magnitude, but they are not in the same direction, so they're not the same. So you can, as you can see, in uniform circular motion, it has constant speed, but changing velocity. That's the first speciality. The second one is we already told you the changing velocity. It has changing velocity in circular motion. Changing velocity, CITY, which means it got acceleration. And we call this type of acceleration centripetal acceleration. And there's actually a formula for it, which is A is equal to v squared over r. The v squared is the instantaneous speed at one point on the circle. For example, at this point, the instantaneous speed is v1. At this point, the instantaneous velocity of at this point is v1. The instantaneous velocity at this point is v2. So, and r is the radius from this point to the circle, or yeah, basically just a radius. So this is a formula for the centripetal acceleration. Also, one thing that is very important is the centripetal acceleration will always pointing towards the center of the circle. For example, at this point, the acceleration will point at the center of the circle, which is right here. At this point, it will pointing at the center. The acceleration will point at the center of the circle. They're all the same. Also, in uniform circular motion, all acceleration, all a's, are you supposed to use this a instead of just normal acceleration. So, which means the Newton's second law, I would just use Newton. Well, actually, yeah, Newton's second will become net force F is equal to mass times acceleration. In circular motion, it will become m times v squared over r. The third one is it. I already told you before previously. It got acceleration, right? It got acceleration, which means it definitely have a force. It need a force because the net force is not zero. And this force is equal to this force is called centripetal force. Centripetal force. We will use Fc to represent it. Also, this force will always point towards the circle or the center of the circle. Yeah, just like this. At this point, the centripetal force is pointing toward the center of the circle, although this is not a circle because my drawing is awful. At this point, the centripetal force will point towards this center. At this point, it will point towards right here. Yeah. Also, as long as an object is doing the motion on a circular track, or as long as an object is doing circular motion, it has centripetal acceleration and centripetal force. Also, another very, 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 very important thing you have to be careful is do not, do not draw centripetal force on your free body diagram. Because centripetal force is actually not a force that something act on it. It's like a net force of several forces that combine together. So again, don't draw it FC on your free body diagram. In AP Physics 1, these are the forces that can act as centripetal force. The first force is right here, the gravitational force. The example is the Earth around the Sun. Imagine this. This is the Sun. This is like a top view of the Earth orbiting around the Sun. This is the Sun. This is the Earth. Yeah, it's not drawing scale, and it's moving in a big circle like this. It is doing centripetal motion because this orbit is basically a circle. Although I draw awfully, this is a circle. The only force that acts between the Sun and the Earth is a gravitational force, and it is pointing towards the center. Basically, it's just a sun. So the Fg is a centripetal force. So Fg can be the centripetal force. That's one. The second thing is tension, which is Ft. The example is spinning a marble with a rope. Imagine you hang a marble at the end of one rope, at one end of the rope, and you're holding another end of the rope. Yeah, you're holding it, and it's going in a circle motion like this. And the centripetal force is from this point. It's just a tension force because the only force to act on it is the gravitational force, which is not pointing towards the center of the rotation center, which is over here. The only force that pointing at that direction is a tension force, which means the tension force is the centripetal force in this situation. The third one is turning car without slipping. Well, yeah, a turning car without slipping. If there's no, if there's because if there's no friction force, the car will basically just slide away, and the tire, the friction between tire and the ground is just pointing towards that rotation center. So just remember that friction turning can be the centripetal force as well. The last force you will see is the normal force. Is the example is like a roller coaster on a circle track. this is the circle track, and then your roller coaster is like, let's assume it is at this position. I will not draw the wheel because it's my drawing is awful. Yeah, normal force is just perpendicular to the surface, it touched, and it is perpendicular to it, and it is pointing towards the center, of the circle, which means normal force will also be can also be the centripetal force. Let me give you a very typical problem you may see on your test. This is a horizontal track. No, wait, it's not actually a horizontal track. It is like a roller coaster track, and there's like a circle path on this roller coaster track. This is a circle. Don't doubt it. This is a roller coaster with a mass m. This stuff has a height or the radius of r. And at the highest point is point A. It's asking you the minimum speed, minimum velocity actually, for the roller coaster to reach point A without falling off. So let's break it down first. At the highest point, so this is like a top part. This is like a top part of the roller coaster track. It's like this part. Yeah, this part of the graph. So the roller coaster will be like this. This is a roller coaster, and let's draw a free body diagram for it. This is a center of mass for the roller coaster. There will be a gravitational force pointing downward. However, the normal force for it is actually also pointing downward because the surface is up here. It's right here. And the surface is giving the roller coaster force to pushing it downward, which means the normal force will also pointing downwards. It has the same direction as Fg. Let's assume the downward is the positive direction in this situation. So let's write a net force equation first. Net force F is equal to Fn plus Fg, and is equal to ma. MAC actually, the centripetal acceleration. Do you remember previously I told you the formula for centripetal acceleration is v squared over r. So plug it in, which is mv squared over r. So it is asking you the minimum speed to reach the highest point A of the circular track without falling off. So at the top part, without falling off, which means at the top part, it barely stay on the track, which means it is like almost falling off. It has like almost no contact with the circular track, which means the Fn will be close to very close to zero. So it's basically just zero. Because it is zero, let's put it in to this formula. Net force is just equal to Fg, and it's equal to mv squared over r. And this velocity is the velocity we trying to find, which is a minimum speed. So let's simplify this equation. Fg is equal to mg. The m is just a mass for a roller coaster, so let's cancel that out. So that velocity we're gonna get is basically just square root g times r. That's it. You can just basically just plug the number, whatever is 9.8 or whatever, and times the radius over here of the circular track. But sometimes it will give you the value of the diameter of this thing. Remember to divide it by 2. If it gives you like this, if it gives you like the diameter of the circle track is d, the formula will change it to square root g times d over 2.